just derived from what we just worked on. It's just set up for two substances rather than just one. And so now you've got two materials where one is going to be losing heat and therefore lowering temperature, but the other one will be gaining heat and therefore raising temperature. The heat exchange between them will be equal, but the temperature won't. Because again, things handle temperature in different ways. Problem number 20. We got a beaker, we got water, and the water starts out at 17.7 degrees. We put in some copper metal, which was at 85.1 degrees initially. The copper is hotter than the water. You put the copper in the water and heat flows from the copper to the water. And heat flow continues until they both reach a common final temperature, which in this case is 23.0 degrees. Both materials will wind up at the same temperature. So we're going to set up what's going on for the water and what's going on for the copper. So for no particular reason, I guess, I'm going to set this up with copper on the left and water on the right. It doesn't matter as long as you're consistent. Specific heat of copper is given in the problem, 0.339 joules per gram degree Celsius. Mass of copper is not given. Mass of copper is what we're solving for. Change in temperature for copper. Copper started at 85.1. It winds up at 23.0, so that is 61.9? No, 60, thank you, 2.1. 62.1. Specific heat of water is a constant. Mass of water was 100 grams. Change in temperature for water. .3. Yeah, 5.3 degrees. And so you've actually got a number for every term but that mass, if you're just careful about where you plug things in. Is there a question about where I've plugged things in? All right, it's algebra from there. You solve toward mass. You're limited to two significant figures because of this 5.3. The temperature change of the water is only 5.3 degrees. That's two significant figures, and by the time you throw that into your multiplication and division, your answer is going to be limited to two significant figures. Go ahead.
Why do you subtract those two temperatures?
That's the temperature change for the water. It started at 17.7 but went up to 23. So it went up by 5.3 degrees. That's how much that's how much the water's temperature changed. Both materials changed temperature. And so you got to calculate each material's own temperature change. And that's really by subtraction. This was the copper, that was the water. You plug things in, you solve through, and it comes up to, with rounding, about 110. Roughly 110 joules. No, 110 grams, 110 grams. Question?
What do you do from there?
From there, you're solving toward mass. So you got to get the mass by itself. You divide these other numbers away from it. So it would be all of this divided by this, this. If you divide those down to the other side, then mass equals all that. Top is multiplied, denominator is division. Question? Any other questions? Do number 21 on your own. this is what it would look like with your numbers plugged in.
Could you get the N number?
The 5.3,
Yeah.
that's the temperature change for the water. You're told that the water starts at 21.3 and winds up at 26.6. Are you getting what you should? Question back. Any question about specific heat at all?
But that one I'm getting 105.3. Is it because it's two significant figures that it's 110 for number 20?
Yes. Now there's two left here, 22 and 23. 22 you can do later on your own. 23, throw it out. We're not going to worry about 23. Cross out number 23. That's a little bit more intricate than what we need to do. So no number 23. So back to the page on atomic structure. In Chapter 2, we're looking at primarily atoms and what they're made of. And ultimately, that's going to lead to calculations involving moles. But first of all, as far as atomic structure goes, theory says that the structure of an atom is 3 smaller particles, protons, neutrons, and electrons. That every atom is composed of various combinations of these 3 particles. If you think of all the zillions of materials that exist, like wood and plastic and whatnot, all of those millions of materials are just different combinations of those 100 and something elements, and it's the proportions of them that make all those materials different. Well, those 100 and something elements are just different combinations of these 3. And it's how many protons and neutrons and electrons you've got that make one particle different from another. We're going to look at their properties, listing them here. These are called subatomic particles because they're below atomic scale. We're looking at them in terms of mass and charge primarily. And mass, we're not looking at grams, but a unit called AMU. AMU stands for atomic mass unit. And it's a unit defined based on atomic structure. So the gram unit is a nice convenient scale for lab work, but it's not a very useful unit when you're talking about individual atoms. And so they made the atomic mass unit scale to talk about individual atoms. And on that scale, a proton and a neutron are each about 1 atomic mass unit. The book will tell you it's probably like 1.0006 and 1.0007. I don't care. They're about 1. All right. They're about equal, and they're equal at 1 atomic mass unit each. Protons and neutrons weigh about the same, and they're defined as 1 atomic mass unit. Electrons are approximately 0. They're not truly 0, as in having no mass, but they're approximately 0, and they don't have much mass, not even compared to the other subatomic particles. The proportions are, it would take roughly 1,800 electrons to equal the mass of 1 proton. And there are no elements out there that have 1,800 electrons, and so we don't have to worry about electrons as far as mass goes. Truthfully, technically, yeah, they do have mass. But it's never a significant amount for us to worry about. The vast majority of the mass comes from these two. Charges, protons have a positive charge, electrons are negative, and neutrons are neutral. And so what you have then, as far as structure, all the heavy stuff is lumped up together in what's called the nucleus. That's your protons and neutrons. And out around that, in motion, doing laps around that, are the electrons. And what keeps the electrons in orbit is opposite charge attraction. Because the protons in the nucleus are positive, the electrons are negative, they continue to orbit around. They don't wander off because of opposite charge attraction. All the heavy stuff is piled into the nucleus, and these electrons, which weigh very little, they're the ones in motion. They're the ones moving around. Question? All right. We'll start an attendance sheet around. Please just sign, please. Characteristics of elements that we need to be able to quantify. Atomic number and mass number. Atomic number. Put a little star by this one. This is the defining characteristic of the element. What makes one element different from another element is the atomic number. And the atomic number is the number of protons in its nucleus. In general, you'll see element symbols written. I'm just going to use generically an X here for some element. But when you're looking at the symbol for the element, every now and then, you'll see a number over at the lower left. Every position around this has a meaning to it. Lower right, we're used to, because lower right would be something like water, where this 2 at the lower right of hydrogen means 2 hydrogens, right? Lower right is the number of atoms. Upper right is positive or negative charge if it has one. But it's these over here we're worried about right now, because it's these over here that are dealing with atomic structure. The upper one is mass number. The lower one is atomic number. And atomic number is how many protons you've got. And if you look at the periodic table on the wall, and for no particular reason, I guess, let's just look at nitrogen. Do you see that 7 above nitrogen? In red, if you're looking at the one on the wall, there's one back there too, they're the same. But if you look at the periodic tables up there, there's a red number 7 above the symbol N. That 7 is the atomic number. So every single atom of nitrogen has exactly 7 protons in the nucleus. 7 protons in the nucleus. That's what makes it different from carbon and boron and oxygen and whoever. Every atom that exists with exactly 7 protons is going to be nitrogen and behave like nitrogen. So sometimes you'll see that nitrogen at the lower right, lower left. Mass number is protons and neutrons combined. Because it's the protons and neutrons that contribute to your mass, right? Both of them contribute to mass, not the electrons though. So if you add up how many protons and neutrons there are, that tells you the mass number. And that will be written at the top left. For nitrogen, it's usually 14. Not always, but usually. Nitrogen is always atomic number 7. It's usually mass number 14. So now we've got a list of atomic symbols here. And we'll come back and talk about the electrons in a minute, but for now, just the protons and neutrons. And we're looking at what this particle is composed of subatomically. We're going to dissect each one of these into protons, neutrons, and electrons. The easy one is the protons, because all we got to do is find that symbol on the chart. Where is it? It's the column on the very left. It's number 11. And because it's number 11, that means 11 protons, period. That number is your atomic number. That number is your protons. The periodic table is laid out numerically, 1, 2, 3, 4, counting on up. That is not an arbitrary order. That order that they're in is based on the protons. So if you know who the element is, iron, copper, carbon, whatever, then the atomic number is a constant. There's no options as far as atomic number goes. The next three are all chlorine. What's the atomic number for them? 17. Go ahead and finish off protons for all of these. Is that what you got? For protons. Not much in the way of options for protons, right? Neutrons. If we look back at this sodium where there's a mass number of 23, that's 23 heavy particles, that's 23 neutrons and protons combined. And we've already said that sodium has exactly 11 protons, correct? So if there's 23 heavy particles in that nucleus and 11 of those 23 are protons, then the rest of them had better be neutrons, correct? Because it's the only thing you've got of significant mass. And so by subtraction, 12 neutrons. Go ahead and finish off the neutron column. Is this what you got? Right. Now electrons then. Electrons being the outer portion, it's the electrons that interact with other atoms. So for example, if that atom were to encounter this atom, if we take the little purple atom and rub it up against the green atom, it's the electrons that make contact, correct? And therefore it's the electrons that can come and go during reaction. Electrons can be gained or lost. And if that happens, then that's reflected in this overall electrical charge that you see at the upper right. Now, if there is no charge showing at the upper right, that means it's neutral. Overall, electrically neutral. And neutral means you got just as much negative as you got positive. So for this first one, where you've got sodium and no net charge, we know already that it's fundamentally got 11 protons in there, right? That's 11 positive charges. So what does that require in terms of electrons in order to cancel that out?
11.
Apparently 11. You've got just as much negative as you do positive, therefore no net charge, therefore no charge showing. The two next ones, where it's chlorine but not charged, that would also be 17 electrons to match your 17 protons, correct? The next one though, this one has a negative charge. Electrons are negative. Having a negative charge means it's got one extra negative than it would normally have. And what's normal for chlorine?
17.
Normal is 17, one extra would be
18.
18. And just to double check, if you compare your electrons to your protons, you've got one extra. One more negative than positive. If you like formulas, then I guess the formula would look like this. The number of electrons would be equal to the number of protons minus charge. So in this particular case, it would be 17 minus a negative 1. And there's 18. Some people just look at it, other people prefer a formula. So if you want a formula, that's a formula. The number of protons minus charge, or atomic number minus charge. What about this aluminum plus 3? You got 3 more positives than negatives, but the positives are unchangeable. So what's the negatives? 10. Iron 2 plus. 24. Iron 3 plus.
23.
And then sulfur 2 minus.
18.
18. All right, good. Question about electrons. I'll go ahead and put formulas up here for all of them, just for people who like formulas. Number of protons equals atomic number. Number of neutrons equals mass number minus atomic number. Number of electrons is atomic number minus charge. All right, at the bottom of the chart,